For me, that means that I'm going to go through the statements, and then I'm going to highlight everything that seems like it's giving me some information about the problem, and then I'm going to translate that into the notation that we have used until now. The first thing is a sample of 24 offshore oil workers. So that means that this over here is my sample that's going to be important, and so I'm going to highlight it. So it took part in a simulated escape exercise. The average escape time was 371.1 seconds, which means that this is an average, and because it's said right after the sample, that means that this is my average escape time for the sample, right? This is the sample average. Then I got a standard deviation of 23.6 seconds, which means that this is the standard deviation also for the sample. This is the sample standard deviation. Then the average escape time the previous year had been 380, which means that I have something is 380. Previous year was 380, and then I'm going to I'm going to have to use a level of significance of 5%. So this is all the information that I have, and that I'll have to translate into the notation that I already know. So the first thing is offshore oil workers. I have 24 of them, so that means that's the sample size for my problem, right? So my sample size is n equals 24. Then I found a sample average of 371.1, so that means the sample average is equal to 371.1. And the standard deviation is 23.6, that's the standard deviation for the sample, which is S, right? So 23.6. I'm going to have to use a level of significance of 5%, so alpha is equal to 5% or 0.05.
You can make them really cheap because it's just the chain with the clip, and I feel like guys like really are into those, you know?
Okay, whoever is getting guys that are something into something, I suggest that you mute your mic. All right, so the next thing is the previous year there had been 380 seconds. That's going to be some value, but I don't know exactly what value this is referring to. Most likely this is going to be a comparison value, right? So this comparison value over here, I'm going to have to think about afterward. All right. Okay, so this is all the information that I have. Now I need to actually try to translate the question that is being asked into a question that I can answer using hypothesis tests. So let me just write this as A over here. And that is going to be the following. So we are trying to determine if the average escape time decreased from this year to the previous year, right? So that means that we have that the average over here is an estimator of a given parameter. That parameter is going to be mu, which is the average or mean escape time this year. And what I'm trying to determine is, so what I'm trying to check, determine, prove, is whether mu, which is the average escape time this year, has decreased from last year, so is smaller than the time from last year, and the time from last year was 380, which means that that value of 380 is the value that corresponds to the comparison number, the comparison value that I'm going to be comparing my mean to. Does this work? If so, please raise your hand.
Wait, so all this really means is the mean has to be less than 380, right?
Yes, so what we're trying to determine is if the actual mean for the whole population is smaller than 380, which is not the same as to say, is the sample average smaller than 380, right? So what we're saying is a sample average of 371.1 enough information to say that the average for all workers is going to be smaller than 380?
Okay, so the 380 is from the year before, but it's all people.
Yes, so it's like the
Oh,
estimate we have
okay.
for last year for all people, so that's like the theoretical value from last year, and what we're trying to see is if the theoretical value for this year is smaller than that.
Okay, okay.
Miss,
Yeah.
I don't understand like how the level of significance of 5%.
Mhm.
I guess it's just the way it's phrased, but like what is that?
Okay, the level of significance is just telling me the amount of evidence that I'm going to need. So this is not really like a number like 3 or 4 that you can interpret right away. This is just telling you, okay, you want to make sure that you're going to be right about 95% of the time. Okay, so what that means is essentially that because you're going to consider rare like rare instances are instances that are in the extreme 5%, and that means that for your sample to give you conclusive results, you'll just have to be in the extreme 5%. Now, if you wanted to be even more sure that your answer is right, you would choose a smaller significance level, which means, let's say, 1%. And so to prove that, that there's a significant decrease, you would have to be in the extreme, not 5, but 1%. So you would need more evidence in order to conclude that. Does that make sense?
Yeah, thank you.
Yeah, so it's just like a measure, like an abstract measure of how much evidence you're going to require before you reach a conclusion. Okay, so this is what we're trying to check, but of course, we have to follow the steps that we follow for hypothesis tests, which are to first determine what you're trying to disprove. So that's what we call the null hypothesis. So we have null hypothesis is that nothing changed. So mu is actually equal to 380. So that the average time didn't change is the same as last year. And HA is the alternative hypothesis. This is that mu actually did change and it was smaller than 380. Okay, so the first thing is just to determine the hypothesis, the thing that we're trying to disprove, which is the null hypothesis, and the thing that we're trying to provide evidence to support, which is the alternative hypothesis. The second thing that we're going to have to do is to determine what the level of significance is. And in your research projects, you're going to have to set your own significance level. But in this specific case, well, the significance level is given to us, so there's really no point in us trying to change it, because then we're going to do it wrong. So that means alpha over here is equal to 0.05. Okay, if alpha is equal to 0.05, again, that's just formulating how much evidence I need. So I just need to make sure that I'm in the extreme 5%, and then I'll be able to conclude. Then, in the third step, we actually have to perform the test, which includes 4 steps. So like 4 sub-steps, 4 pieces that we have to put together. The first thing is to identify the test that you're going to have to use. And this is important more when you have like other types of information at the same time, and then you have to like actually choose between the ones that we have seen until now. But up until this point in class, we have only seen one test, and so that's the only one that we can use. So that's going to be the one sample t-test. Right, so one sample t-test, which is essentially saying, okay, well, I have one sample, and I'm trying to do a test for the mean. Right? The second thing is to determine what the critical value is. And so the critical value is just the number that separates what's normal from what's rare, right? What's usual from what's extreme. So that means over here, we're going to have some kind of distribution. And I'm trying to show that the mean is smaller than 380, so that it's smaller. So that means on the left-hand side, right? So if I'm trying to show that it's on the left-hand side, then that means that my critical value has to be on the left-hand side as well. So it has to be a number over here that splits the extreme 5% from the rest, the usual 95%. Can I see a show of hands for those of you who understand this? Okay, that's not bad. And so we're going to have to look at the table in order to find the critical value over here, which is going to be minus t 0.05. But I have to remember to look at the number of degrees of freedom. And the number of degrees of freedom is always n minus 1, which in this case is 23. So number of degrees of freedom for this test is equal to 24 minus 1, which is 23. All right. So what I do now is...
Sorry, why is that? Is that just because it's the t
That's
test?
given.
So sample
Yeah.
24 minus 1.
Exactly. So it's for one sample, it's always sample size minus 1.
Yeah, but what does the DF stand for?
Degrees of freedom. Nothing that
okay.
you really care about. Yeah. So this is just the degrees of freedom is a measure of how much information you have in your sample, which depends on the size of the sample that you have. But it doesn't really come into play for our class. The only thing that comes into play is what row you're going to be looking at in your table. That's it. So what we're going to do now is go to the table. We're looking for a one-tail test. Oops, forgot to erase everything. So we're looking for a one-tail test that corresponds to a 5%, level of significance of 5%. So that means in the row that says one tail, we're going to go to 5%. And then we're going to look at the row over here that says 23, because that's the number of degrees of freedom that I have, right? So that's why I have a DF over here. And so, yep.
If it was like 50 workers, then it would be the Z table, right?
If we were 50 workers, not for tests, we're not going to use Z for means in any case, then you would have to go to one of these.
Okay.
So just the closest one.
So it's always the T table for these?
Always the T table for our case, just because I didn't want to separate into even more cases, right? So
all right, thank you.
Normally, yes, it would be the Z table, but because I don't want to include like test on test on test, we don't have that much time and, you know, like actual practice time in class, we're simplifying things quite a bit this semester. Okay, so then we have row for number of degrees of freedom 23, column for 5%, and one tail, and that means that my value is 1.740. I can go back now with that value, whiteboard. And so that means that this number over here is 1.714, but it's on the left-hand side, so that means that this is going to be minus. Show of hands for those of you who understand. Okay, everybody hands down. Now, show of hands for those of you who do not understand how I found this value. Okay, so again, what I did is I'm looking for the value that separates 5% from the rest of the 95. So that means the rare 5% from the rest of the 95%, the more usual 95% of values. And so what I have to do is, because I'm looking at a one-tail test, I'm only chopping the bottom 5%, not the bottom and top. And that means I'm only chopping information from one tail. That's why we talk about one tail. So we go to the row over here that says one tail. Our level of significance is 5%, so 0.05. So I know I need to look in this column over here. And then because my sample size is 24, then 24 minus 1 is 23. And so I need to look at this row precisely, which gives me the number 1.714. So the number 1.714, what it's doing is separating the rare information from the usual information, right? So this is what I should usually expect if the mean were actually equal to 380. And this bottom over here is what's rare. Okay, what's extreme. Now, this is my critical value, which means that, let me just write that down. I'm going to have minus t 0.05 and 23 is negative 1.714. And the next thing is, okay, now that I've differentiated between what's usual for a given sample and what's rare, what I'm going to do is look for my specific sample, what value did I get? And then I'll conclude based on whether I got a rare value or a usual value. If I got a usual value, then that means that my result was to be expected from a sample whose mean was 380. Whereas if I got an extreme result, that means that it is very unlikely that my sample was produced by a population whose mean was 380 seconds. And so most likely, the mean was actually smaller than 380 seconds. Okay, so I'll find the value for t over here. So the second, the step C over here is the test statistic. And this is based on what we did last class, so you should have it in your notes. The formula for t is equal to x bar minus mu naught, which is the comparison value. Mu 0 is the comparison value, divided by s over square root of n, which if I replace with the values that I know is going to be 371.1 minus 380 divided by 24. 24? No, not yet. Not 24 yet. Divided by 23.6 over square root of 24. I think this value is something like negative 1.85, I believe. All right, so I have a value of 1.85, negative 1.85, which means that from my sample, assuming that I started from a population whose mean was 380, negative 1.85 is somewhere around here. It's smaller than 1.714, right? It's somewhere around here, which means that my sample actually is in the rare side of my distribution, which means that it was very unlikely that I got such an extreme result, which kind of makes sense with what we're seeing. Right? If my original escape time was actually 380, it is very unlikely that for a sample of 24 workers, my average had been 371.1 seconds. Right? And so most likely the actual average was smaller than 380. Does everybody understand this? If so, please raise your hand. Okay, slowly but steady, hands raising. Are there any questions? Yeah, okay. So what I have is, I'm sorry, Alex, can you repeat your question?
Yeah, just so I can process it one more time, may you repeat it?
All right, okay. So what I have is a sample from which my test statistic was negative 1.85, whereas I said that if the average had actually been 380, the value that would have split the usual values from the extreme values would have been negative 1.700.
Ah, yes.
Yes, so that means that if I have a value that is smaller than that, that is a value that is rare, it's extreme, because it is very unlikely that if my actual mean for this year is 380, then from a sample of 24 workers, I get a sample average of 371.1. Most likely what's actually happening is that the average time for all workers is smaller than 380. That might mean that the actual sample for all workers is 371 seconds, but it might also mean that it's 375 or 374. I don't know. All that I have evidence for is that it is most likely smaller than 380. Does this make sense for everybody?
Miss?
Yep.
Why is it, or like if it's before the line in the middle, is it negative? Like why is the t negative?
Oh yeah, it's because it's on the left-hand side, on the left side of the distribution. So if it's before that, it's negative. If it's above that, it's positive.
Thank you.
Yep. All right, and then that means that our original assumption that mu was actually equal to 380 is no longer a reasonable explanation, right? It can't account for how extreme a result we got. And because it can't be a reasonable explanation, what we say is that we reject the null hypothesis. Oops, reject. H naught, and so that means that it looks like we have enough evidence at the level of significance of 5% to say that the time, the average time, escape time, decreased. Now I have to specify the level of significance, because the whole point, the way that I found my boundary between what's usual and what's extreme depended on that 5% that I chose. If I had chosen maybe 1%, then my boundary would have been different, and maybe I wouldn't have had enough evidence, right? So it all depends on how much evidence you require in order to reach a given conclusion. Right, so that brings me to question B, which asks, explain why you cannot be completely certain that your answer to A is right. Question B, what we're gonna say is, okay, maybe finish writing and raise your hand when you're done writing. Okay, so for B, the question is, why can't you be completely certain that your answer is right? So the answer for us in A was, there is enough evidence, and we conclude that the average escape time did decrease, right? So essentially our answer for A is, yes, the time decreased from one year to another, but we can't be certain because there's still that very slight chance. It is still possible that you had an average for this year of 380 seconds, and just out of luck, we ended up choosing the 24 offshore oil workers that had escape times that were lower. If that is the case, if we just happen to choose at random oil workers that were faster at escaping, then that means that our sample, without us knowing, is not as representative of the population, and so our conclusion would have been wrong, our data would have been misleading. There's no way for us to know that. There's no way for us to know if our sample is getting us the perfect estimate for the parameter, if it's getting us a more or less good estimate for the parameter. What I can say is there's still that slight chance that I just happened to be in, that I just happened to select a sample that was slightly off. Okay, so there is still a chance. Although I know that my chance is less than 5%, because I'm in the extreme 5%, there's still a chance of less than 5% that my sample did come from a population whose mean is 380 seconds, but produced a very small sample average. Right, so that's still a possibility, and we have no way of knowing. All that we can say is, okay, everything that I conclude comes with, you know, that little disclaimer over there that there's still a little chance that I made a mistake unknowingly, because I can never know if my sample is perfect or if it's maybe a little bit further away from the mean. Even if it's perfectly chosen, that can happen. Remember, a couple of weeks ago we had the homework on variability of statistics, where you said, oh, actually, we chose our sample perfectly fine with the heights of women in Pumpkinville, and still some people got averages that were just a little bit too far away from the actual value. Right? So that's still something that can happen. Can I see a show of hands for those of you who understand and are done writing? Okay, so what we're going to do today is look at two new hypothesis tests about two different types of estimation that we're trying to do. I'm going to do probably just one example for each of them. Hopefully, I'll be able to finish the last example, and then that will be it. Okay, so here we go. Next test. The next test is what we call a one sample test for proportions. And in the same way as for all other tests, we have to have some assumptions. We're going to have to formulate our null hypothesis. And we're going to have to formulate the test statistic.
What exactly is the null hypothesis for?
The null hypothesis is the thing that we're trying to disprove. So it's always the thing that we assume to begin with, and then we provide evidence to counter.
Okay.
Okay. So for example, here our null hypothesis is that the mean was 380. And what we're trying to do is with our data say, no, actually the mean is smaller than 380. So we're always trying to contradict the null hypothesis.
Okay. Okay.
Yeah. All right, so for us to be able to use this this test, and that's always what I mean by assumptions. It's just like what are the strings attached? What do I have to make sure is verified? Our assumptions here are simple. They're just that n times the comparison proportion. I'll talk about the comparison proportion in a second. No panicking yet. Is larger than or equal to 5, and n times 1 minus the comparison proportion is larger than or equal to 5 as well. That's just, you know, some work that we have to do. We need to make sure that this is the case, and that's it. The null hypothesis is the thing that we're actually going to try to disprove, right? So we're going to always start with the same type of assumption, which is H0 null hypothesis, which tells me that the proportion that I'm going to try to estimate, and this is the parameter that we're going to be hypothesizing about this time. We're going to try to show something for a given proportion, but we're going to always start with the assumption that that proportion is equal to a certain number. Okay, so a certain number, that just means the comparison value, which is P0 or P0. Okay, so this is comparison value. Then the test statistic here is going to be related to the distribution for proportions, and this is equal to, so it's Z, which is equal to P hat minus P0 divided by square root of P0 times 1 minus P0 divided by N. Okay, so this is where P hat, excuse me, where P hat is equal to X over N. So X being just the number of items that have a certain characteristic. So you can think about, for example, if you're estimating the proportion of people that voted conservative in the last elections, then p hat would be number of people that voted conservative divided by sample size, so number of people that voted. Does this make sense for everybody? Questions, comments? All right. So we have something that we want to disprove. We have the number that we'll have to compute in order to disprove this. And just here for a second, realize that the form of each one of my test statistics is always the same, which is estimator minus comparison value divided by the variability of the sample. Same thing over here. Estimator minus comparison value divided by the variability of my sample. It is the same exact thing, it's just that different parameters have different distributions. Then what I need to determine is, what am I trying to show? What are my alternative hypotheses? Alternative hypothesis. And depending on what the alternative hypothesis is, I'm going to reject under different conditions. Right? So if I'm trying to show, I'm trying to provide enough evidence to say that the actual population proportion is larger than the comparison value, then I'm going to reject the null hypothesis. I'm going to have enough evidence if I get a large enough proportion, right? So if I'm, if I get a large enough proportion over here. Now, this one over here is a Z test. Okay, Z test, which means that this is going to be Z alpha, or of course this is equal to alpha. So everything depends on the significance level that I choose. The more information, so the smaller the significance level, the more evidence I require in order to contradict my null hypothesis. Then, if HA, if the alternative hypothesis is that P is smaller than P naught, that means that I'm going to have enough evidence if my result is small enough. It's enough on the extreme side, but on the small extreme side. That means I'm going to have enough evidence if I'm somewhere around here, where again, this is alpha, and so this is going to be minus that alpha. And then if my alternative hypothesis is that P is different than P naught, than the comparison value. So maybe I don't care about whether a given proportion is larger than some proportion or smaller than some proportion. I just care about determining if it's different than a value. Then I'll have enough evidence to contradict my null hypothesis if I have either a very small value or a very large value, right? So this would be minus Z alpha over 2 and Z alpha over 2, because again, I can only look at the extreme alpha percent, so that just means that the sum of these two should be equal to alpha. So that means that here I'll reject H naught if what? Well, if my test statistic is larger than Z alpha. All right. Then reject H naught if Z is smaller than Z alpha with a minus in front. And for the last case, I'll reject my null hypothesis. I'll have enough evidence to contradict my null hypothesis if either Z is larger than Z alpha over 2 or Z is smaller than minus Z alpha over 2. Does everybody understand this? If so, please raise your hand.
Miss, not really.
Okay, so where did I lose you?
I think the different like H or like the P's, like I don't really understand what they mean.
Okay.
On the left side.
So depending on the case that you have, depending on the example that you have, you're going to be showing either something is larger than a given value, smaller than a given value, or different than a given value. Right? So for example, in the previous case over here, I'll be back to the other slide. In this case, we were trying to show that the mean was smaller than 380. But sometimes we'll show that the mean is larger than a given value. or that the mean is different than a given value. We can do the same thing for proportion. So maybe I want to show that, I don't know, more than 33% of Canadians voted for conservatives, okay? And then I'll take a sample and I'll try to show that more than 33% of Canadians voted for conservatives. So then when would I have enough evidence to say that more than 33% of Canadians voted for conservatives? That would be if I had a large enough result. If I had a large enough proportion, then that's when I would conclude that, right? If I wanted to show that the proportion is smaller than a given value, I would have enough information if I had a small enough value. And if I want to show that the proportion is different than some number, then I'll have enough evidence if it's either much larger than that number or much smaller than that. Does that make sense?
Yeah, it does. Thank you, Miss.
Right. Okay. So the rest is just really technicalities, right? So how do I show it? But keep in mind always the idea of this, because you'll always have a table that you'll be able to refer to. So you'll have your notes. You'll have, I'll post eventually once I'm done with the grading and everything, a formula sheet for all the tests that we're seeing in class. And so what's really important is for you to understand the logic behind it, and then after that you're done. Okay, so what I really want you to understand is how it works, what the mechanics of the tests are, and that's it, right? The rest is really just plugging in values. So here we go. We're going to do an example for proportions, and then the next type of test, right? Actually, can you please raise your hand if you're done writing? Keep your hand up. Just want to make sure that everybody has this, because it's kind of the important part here. Okay, 20 more seconds, so be fast if you haven't finished yet.
Miss Bottom right, that's an over 2, not a 12, right?
Over 2, yeah.
Yeah.
Does look like a 12. All right, so in the next example, we have that studies in psychology show that 50% of normal babies age 12 months walk, and at 12 months, 30 out of 80 premature babies walk. What we want to determine is if there's enough evidence to show that there's a delay in development for premature babies. We're going to test the hypothesis of the 2% significance level. I'm doing the same thing as in every hypothesis test problem, which is to try to look at all the information that we're given and summarize what it corresponds to. So I have a 50% of normal babies over here. That might be helpful at some point. And then I have the 30 out of some number. So I have 30 is one of the pieces there. And then 80 premature babies are walking. And then I'm trying to determine if there's a delay in the development. Delay in the development. So I'm just going to underline that for premature babies to remember that that's what we're trying to show. And I need to test the hypothesis with a level of significance of 2%. So 2% significance level. So as usual, I try to summarize all the information that seems clear, and everything else I keep, highlighted over there to see if and when I'm going to use it. So the first thing is I have 50% of normal babies walk. Okay, so this is apparently something that we know, something that is known. Then if we think about the actual sample that we have, the sample that we have is 80, right? So 80 premature babies. So we have that, my sample is a sample of premature babies, and I have n is equal to 80 in that sample. Okay. Then from that sample, I have that 30 have a given property. What property? Well, they walk. So 30 out of these 80 walk. And I have that alpha is equal to 0.02. Okay, so based on the sample that I have, there is a proportion that I am able to evaluate, p hat, which would be 30 over 80. Okay, now that's just by being mechanical and understanding that I can compute this this proportion, which is going to give me 0.375. But more importantly, what this represents is the sample average, sample proportion of premature babies that walk, right? Premature babies that walk. Now, if this is the estimator that I'm looking for, then that means that the proportion that I'm actually interested in estimating and doing a test about is going to be the proportion, so the population proportion of premature babies that walk. Proportion of premature babies that walk. Of 1 year old, like 1 year old that walk. Does everybody understand that? If so, please raise your hand. Okay, so now this is the proportion about which I can conduct a test. Now what I need to determine is what test I'm actually trying to conduct here. So what I'm trying to show, check, verify, give evidence for is whether there is a delay in development. Right, so I'm trying to check if there's a delay in development. Now, that's a very vague question, a very open question, but what we can do is take that conceptual question, is there a delay in development, and translate it into a question that we can answer quantitatively based on the proportion that we have over here. Now, knowing that for normal babies, full-term babies, 50% of them walk after 12 months, then what would be the corresponding thing that we want to show if we want to show that there's a delay in development for premature babies? Anyone? If there's a delay in development, the proportion of premature babies that are 1 year old that walk is going to be what? It's a delay with respect to what? So if I'm trying to determine that there's a delay in development for premature babies, it means that I'm saying that some number is different than some number. Now, I know that 50% of normal babies walk after 12 months. If there is a delay in development for premature babies, what's going to happen with the proportion of babies that walk after 1 year old? What can you say about it if there is a delay?
It's going to decrease.
It's going to be smaller than 50%, right? If there is indeed a difference between full-term babies and premature babies in terms of development, then that means that after 1 year old, premature babies should not be at the same place, and so there should be fewer premature babies that walk than normal babies that walk, right? So that means that if this is what I'm going to check for, then I'm implicitly checking for whether the proportion of premature babies that walk, P, is smaller than 0.5, which means that that 0.5 is actually our comparison value. Can I see a show of hands for those of you who understand this? All right. So same steps as usual. Start with a null hypothesis. Thing that I want to disprove, which is always an equation. And so here I want to start from the idea that P is equal to 0.5 so that there's actually the same, so like the same proportion of premature babies as full-term babies that walk after 1 year. So the proportion is equal to 0.5. And the thing that I'm going to find evidence for is that P is smaller than 0.5. Right, so that means that the proportion is actually smaller than 0.5. There's fewer than 50% of PEs that walk after 1 year. The second thing that I'm going to do here is to be explicit about what the level of significance is. That's not too bad because I was given that significance level. That's 0.02 or 2%. Then the third step is to actually do the test, which means 4 things. Decide what the test is, find the boundary point, find a point for my sample, and conclude. Always the same 4 things. Okay? So determine the test. Well, I just have 1 sample, I just have 1 proportion, right? So this is a 1 sample proportion test. Then I need to check for the boundary point, which means the critical value. This is not the same as in calculus. So critical value has another meaning in QM. So this is just the boundary point between what's extreme and what's usual. So that means if I look at my distribution like this, then what's extreme in this case, I will have enough evidence if the proportion for the premature babies is small enough, right? So if I have a small enough value over here, oops, over here. And so that means that this is what I'm trying to look for, where this is 2%. Does everybody understand that? Please raise your hand if you do. All right. And so if I want to separate the bottom 2% from the top 98%, I'm going to have to go to my table. But in this case, this is a Z table. So I'm looking for minus Z of 0.02, which means you share photos, which means I'm going to look for the value in the Z table that is the closest to 0.98, right? So I'm looking for 0.98 over here. I get 2.05. That's the value that separates the bottom 98% from the top 2%. Now, if I want the bottom 2% from the top 98%, I'm just going to have to take minus 2.05. Okay, so I go back over here and I get that this value over here is equal to negative 2.05. That's the value that separates the bottom 2% from the top 98%. Okay, so Z 0.02 is equal to 2.05, which means that minus Z 0.02 is minus 2.05. Then I can evaluate the number for my, I can evaluate the test statistic, which is going to be just Z, which is equal to P hat, that's 0.375, so always estimator, minus comparison value, so 0.5, divided by variability, which in this case is given by 0.05 times 1 minus 0, no, sorry, 1, there you go, 0.5 times 1 minus 0.5 divided by n, which is equal to 80. And if you plug this into your calculator, you'll find negative 2.24. Does everybody understand this?
Quick question.
Yep.
Why did we use the negative z instead of a positive z? Why does it have to be a negative?
It's negative because we're checking if the proportion is smaller than a value.
Ah, okay, okay.
Yeah. Okay, and so now because we have a value over here, negative 2.24, that actually falls within our rare values, right? So the usual values are everything above negative 2.05, the rare values are anything below, and negative 2.24 is below. Then we have that our result is too extreme, and so we can reject the null hypothesis. So reject the null hypothesis is just like the automatic way of answering the question, but what we're actually saying is that there seems to be enough evidence to conclude, to say that there is a delay in development. Right, and that's, so there's enough evidence to say that there's a delay in development with alpha is equal to 0.02. And again, it's important to specify what the alpha is because that tells you how much evidence you're required to begin with. Okay. Does everybody understand this? Please raise your hand if you do.
Miss,
Yep.
why did we use a Z table? I thought we were only using T tables.
Because the Z table is what we use for approximations for proportions.
Oh, okay.
Mm-hmm.
So it's for the formula, I guess?
Yeah, so it's just, I mean, the justification of this goes into heavy statistics. So for now, you just have to believe me. Whenever it's a proportion, we're going to use a Z table.
Okay, thank you.
Okay, and so based on this, is there a chance that your conclusion was wrong? So we concluded, yes, there's a delay in development. Is there a chance that your conclusion is wrong? Yes, of course. There's always a chance that I made a mistake. Because there is still the possibility that my sample comes from a population of premature babies from which 50% walk when they are 1 year old, but the sample that I chose of 80 premature babies actually just happened to be a sample in which babies hadn't yet walked, right? So maybe I just happened to choose a sample that had fewer babies that had walked, even though in the population, maybe the proportion was equal to 50%. I don't know, I can't know. Does everybody understand that? Questions, comments? All right, so I'll give you maybe 45 seconds to finish writing this, and then I'll go on to the next test, which is the last one that we're going to look at for means. It's also the most interesting one, though. Yeah, it was on camera. Okay. So for the next test, I'm going to look at a little bit of a different case, which is the following. I'm just going to erase part of this. So because we always have the same type of format, I'm just going to keep a bunch of the information over here for the test that we're going to have. So the next test is a test that is more interesting because it allows us to compare two different samples. So the reason that I've been talking about one sample test is that sometimes we can have tests that work for 2 samples or for more samples, but we're going to talk about 2 samples today. So 2 sample test for means. That means we're going to test for differences between 2 samples. Okay, so what we're going to try to test for in this case is the difference that there might be between averages of something between 2 means. This is something that is particularly interested, for example, if you're looking at an experiment and you want to see a difference between a treatment group and a control group, right? So for example, imagine that you're doing an experiment about, I don't know, a training program. So you have 2 groups. One of your groups is doing one training program and the other group is doing another training program. And then after 1 month, you're going to look at the average weight that each one of the groups can lift. So maybe you want to measure that, compare them, and then whichever group can lift a higher weight, you're going to say, okay, maybe that's the training program that is better, right? So you want to look at differences in averages between 2 groups. The idea here is to say, okay, well, differences in averages between 2 groups can be due to a bunch of things. They can be due to random chance. It can be due to sampling mistakes and so on. But assuming my sample is good, I can still expect some variability. Now, how different do my averages have to be, or how large do my samples have to be if I want to actually conclude that there's a difference between the two samples? Okay, so that's what this test allows us to do. As per usual, we have some assumptions to make. We have some strings attached when we try to apply this, this test, which are, the first thing is that the data has to come from approximately normal distributions for both samples. So the data is approximately normal. And I also have that the 2 samples have to be independent. So the samples have to be independent. Independent. What does this mean? It means that whether one sample did well or poorly doesn't depend on whether the other sample did well or poorly. And so the idea is really that whatever happens with one sample has nothing to do with what happened with the other sample. Now, because we're going to be looking at differences between 2 samples, this is a lot more things that we have to take into consideration. And so the formula here is going to be horrific. It's going to be horrible. Lucky for us, we always have the formula at hand. So as long as we know where we have to plug in each of the numbers, it shouldn't be that bad. Okay? So I'm going to call my samples sample A and sample B. Okay? So that means that everything that I label with A comes from sample A, and everything that I label with B comes from sample B. My null hypothesis, so the thing that I'm going to start with, is that the mean for the first sample minus the mean for the second sample is going to be equal to some comparison value, which I'm going to call D. Okay, D for difference. And so D over here is just the comparison value. So this is like the hypothesized difference. So what I think the difference between these two is going to be. And so that's the comparison value, the hypothesized difference. So what that means is I'm going to start with the assumption that this is the difference between my 2 means, and then I'm going to either show that the difference is larger than this, smaller than this, or different than this. Often, this value is going to be 0. Okay, so for example, if I'm trying to show that 2 means are, that one of them is larger than the other, I just have to show that their difference is larger than 0, right? So This is often how we're going to formulate our problems. The test statistic is T, which is equal to the sample average for the first population, so the sample average for the first sample, minus the sample average for the second sample, minus the difference that I think there is between the two values, divided by the standard deviation, the variability of A and B. This doesn't look too bad. That's because I need a whole other line to explain how to compute the variability between SA and B. So this is going to be square root. You can see from the size of the square root that this is going to be a long expression. This is NA minus 1 times SA squared plus NB minus 1 times SB squared. So that means the sample size for the first sample minus 1 times the standard deviation squared for the first sample plus the sample size for the second sample minus 1 times the standard deviation for the second sample. The whole thing divided by NA, the sample size for the first sample, plus the sample size for the second sample, minus 2. And then after computing this whole number, you're going to multiply this by 1 over the sample size for the first one, plus 1 over the sample size for B. There you go.
Oh, sorry.
Yep.
I thought I was muted.
No, I'm pretty sure you're just expressing everybody else's feelings as well.
There's no room on my paper to write it.
Yeah, probably on the notebook too. Anyway, this is going to be provided to you like in a formula sheet, but just make sure that you copy it down now and that you copy it right. Reread it several times because there's so many opportunities to make typos. And for precision right away, I'm going to also specify how to compute the degrees of freedom. It's not that horrible. It's just NA plus NB minus 2. Okay, so when you're trying to determine which row to look at in your T table, you just have to compute it by doing NA plus NB minus 2. Okay, so this is just for the degrees of freedom. It's just a small calculation that you need to do in order to figure out which row to look at. Again, keep in mind that the goal for me is not to make you apply like horrible formulas. Occasionally, I will give you the statistics that you need to use. But you know, this is a formula. This is what's behind this number that you're given, and so you need to know that this is the formula. That's it. You're given its value in formula sheets whenever you need it. All right, so what we're trying to determine is whether there's a difference between mu A and mu B, whether that difference is larger than D, smaller than D, or different than the value that we hypothesized it was equal to. And so we have different alternative hypotheses, which are mu A minus mu B. So maybe I'm trying to contradict that it's equal to D by saying it's actually larger than that number. Or maybe I'm trying to contradict that is equal to D by saying it's actually smaller than the number that I started with. Or maybe I don't care about whether it's larger or smaller than that number. I just want it to be different than that number. Okay. And this is the same as usual, except here we have a T distribution. So this is T alpha. This is minus T alpha. This is minus T alpha over 2. And this is T alpha over 2. Do I have any questions?
Yeah, sorry, Miss. On the right side of the top graph or on any of the graphs,
Mhm.
is the loop thing, that's not a D, that's not the D, right? Or is
No,
it?
that's alpha,
That's a separate thing.
the significance level, yeah.
Miss, I was writing
Yep.
down the wrong formula. What's the DF?
DS is just the degrees of freedom, so it's the way for you to find what row you have to look at in the t-table. Right?
I'm not sure I understand.
So when you have a one sample t-test, you always do sample size minus one, right?
Okay.
So that's how we've done it up until now. Now, in this case, I'm saying, okay, if you have two samples, the degrees of freedom are calculated a bit differently. You just have to do sample size for the first sample plus sample size for the second sample, the whole thing minus two.
Oh, okay.
Yeah.
Thank you.
Yeah. And so here, the conclusion is the same. You'll reject H0 if your t-value for your sample, your test statistic, is large enough, so larger than t alpha. If you're trying to disprove that it's equal to D by saying it's smaller than that value, then you'll reject H0 if this is smaller than minus T alpha, so if it's small enough. And then here you'll reject H0 if either T is larger than T alpha over 2, or if T is smaller than minus T alpha over 2. Is that okay? Please show your hand if you understand. At this point, it's just a repetition from what we did before with the proportion. But with, ooh, what was that? With two samples. So when you're done writing and you think you're pretty good with understanding this, please raise your hand. Okay, I still have Carolyn, Chloe, Shauna, and Victoria who don't have their hands up. Is that because you are not done writing? All right. Okay, I think we're pretty much okay then. All right, so I'll start the next problem with respect to this. I think the main thing here is to try to formulate the hypothesis. I think this is the more difficult part for this test, which is to try to say, okay, what's my null hypothesis? What's my alternative hypothesis? And then once you have that, it's just a matter of plugging in all the pieces that you have into your formula. It looks horrible, and it is horrible, but it's just a matter of plugging in, right? So as long as you're good at using your calculator, you should be fine. So there we go. We're here, okay. So a group of statistics students are asked to measure their middle fingers, and we are going to try to determine whether there's a significant difference in the lengths of middle fingers between women and men. Why? It's a puzzle. The results are summarized below for male students and female students. That means we have that data was collected from 16 men and 11 women. From the 16 men, there was an average middle finger length of 109.94 millimeters. And for females, for the 11 females, there was an average length of 98.55 millimeters and a standard deviation of 6.01. The whole point of this is to determine whether this is enough of a difference or not, right? Because we have that, sure, there is a difference. This is 109 and this is 98. We're not done. We know that there's a difference between these two. The question is to say, okay, well, is this a difference that is only caused because of just random variation that I can expect between my samples, or is this an actual indication of the fact that middle fingers have different lengths between women and men? Okay. Can I see a show of hands for those of you who understand the point of this test? All right. So I'm going to call the sample for males sample A and the sample for females sample B. And essentially what that means is that N over here, that's the sample size for male. So this is NA, this is NB. This is X bar A, this is X bar B, and this is SA, and this is SB. And so that's all that I'm So what I'm trying to show, I'm trying to prove through evidence that there is a difference between mu A and mu B, where mu A and respectively mu B is the length, so the average length of middle fingers for males. And mu B is the same thing, but for females. Now, I'm trying to show that mu A is different than mu B, which means that this is going to correspond to my alternative hypothesis, right? So this is the thing that I'm trying to show evidence for. But my alternative hypothesis, as well as my null hypothesis, are all expressed not in terms of mu A and mu B, but in terms of mu A minus mu B, in terms of the difference between these two means. That means that if I'm going to look for information that proves or disproves this by using the test that I just formulated, I'm going to have to express this as a hypothesis based on mu A minus mu B. So that means that my alternative hypothesis should actually be about the difference between these two values. And so that means I'm going to have mu A minus mu B is different than 0. This is the alternative hypothesis, what I'm trying to show, which means that what I'm going to start with, the null hypothesis, is going to be that mu A minus mu B is equal to this value. Does everybody understand this? Yeah, so I'm going to start with the assumption that mu A minus mu B is equal to 0, which means that the mean length of middle fingers and the mean length of middle fingers for males and for females, when I subtract them, they give me 0, which means that they start being the same. And what I'm going to try to do then is to show enough evidence to say that mu A minus mu B is different than 0. Does everybody understand this? Can I see a show of hands for those of you who do understand this? Okay, do I have any questions? No questions? Okay. So then what you're going to have to do is, oops, I don't think I gave you an alpha over here. So use alpha is equal to 0.01. That means in the next step, you're going to have to use alpha is equal to 0.01. And then for step number 3 over here, you're going to have to follow the same steps as before, which means decide the test, find the boundary value, find the value for the sample, and then conclude. So same 4 steps that we've been using by using the test that we just developed, right? So we already found the, yes?
I have class, I need to.
Yes, no, absolutely. I'm finishing this in a second.
Okay. Right.
Yeah, of course. So all that I want is for you to finish this problem at home. That was how I was going to finish this over here. You just have to apply the steps that you need to do. So those 4 steps, you apply them by using this test, and then that's it. The rest is just mechanics. You just have to plug in everything that you have. So by Thursday, I want you to finish this problem and practice as many as you can from the practice problems of hypothesis tests. The more you have practiced by Thursday, the better, because we're switching gears, we're changing into something else, and so it's better to have practice by then, and then hopefully you won't forget after that class is done. So have any questions about it?
So is this our homework?
yeah, so just finish this problem up, and then there's the practice problems that I posted on Leah, which are called, I think, practice problems for hypothesis tests. You can do as many as you can from there. I'm posting solutions for those as well.